Hello, viewers. In today's session, we are going to discuss an important and conceptual problem from logarithms of complex quantities, right? And we have already discussed the concept of logarithms of complex quantities in one of our videos. So here we are going to solve an important problem related to logarithms of complex quantities. So here we have to find the principal and general values of log of minus 1 plus iota to the base e, right? So here we have a complex number that is minus 1 plus iota, and we have to find out the principal value and the general value of the logarithm of this complex number, that is minus 1 plus iota. So before finding out the principal and general values of the logarithm of this complex number, let us first convert this complex number into a polar form, right? So here we'll first convert this complex number into polar form, and we'll assume z is equal to minus 1 plus iota, that is x plus iy, right? And we can write x plus iy as r, and here we have cosine theta plus I sine theta. So here we are using the usual notations. So this complex number z is equal to minus 1 plus iota, then we can take it as x plus iy, that is equal to r times cosine theta plus I sine theta, where theta is the argument or the principal argument or the principal value of the argument of this complex number z, right? So here theta is the principal argument, that is denoted by argument z, right? And here if we compare these two complex number, then we have x is equal to minus 1 and y is equal to plus 1. And if we see the complex plane here, this is the real axis, this is the uh, imaginary axis, and this point, that is minus 1 comma 1, it lies in the second quadrant. So here we have minus 1 comma 1, that is x comma y. So our complex number z, it lies in the second quadrant. So here we have minus 1 and here we have 1. So this is our complex number, that is z, right? So the argument of z when the complex number z belongs to the second quadrant is given by pi minus tan inverse of y divided by the absolute value of x, right? So theta is given by this expression. So now if we compare these two complex number, then x is equal to r cos theta, y is equal to r sine theta, and r cos theta is equal to x, that is equal to minus 1, and here r sine theta is y, that is equal to plus 1. So squaring and adding, we have r square cos square theta plus r square sine square theta is equal to minus 1 square plus 1 square, that is equal to 1 plus 1, that is 2. And here we have r square cos square theta plus sine square theta is equal to 2. And by trigonometric identity, this expression is equal to 1. So we have r square is equal to 2, that is r is equal to square root of 2. So from here we can see that r cos theta is equal to minus 1. So cosine theta is minus 1 over r, that is minus 1 over square root of 2. And from here we have r sine theta is equal to plus 1. Sine theta is equal to 1 over r, that is 1 over square root of 2, right? Okay, so now if we now convert this complex number z into polar form, then we can now write z is equal to square root of 2. Here r is square root of 2, and we have cosine theta plus I sine theta. Right now, theta is given by this expression. So now we can write here a pi minus a tan inverse, and the value of y is equal to plus 1, and the absolute value of x, that is mod x, is equal to mod of minus 1, that is simply 1. So here we have 1, so we have pi minus tan inverse 1, and tan inverse 1 is pi over 4. So we have 4 pi minus pi over 4, that is 3 pi by 4, right? So we know that tan pi by 4 is equal to 1. So pi by 4 can be written as tan inverse 1. So here the value of the principal argument is given by 3 pi by 4. So our theta is 3 pi by 4, and here we have I sine 3 pi by 4. Now using Euler's formula, we have here square root of 2, and this expression can be written as e raised to I and 3 pi by 4, because e raised to iota theta is given by cosine theta plus I sine theta, right? So our complex number, that is minus 1 plus I, is now given in this form, that is square root of 2 times e raised to I times 3 pi by 4. So here it is important to note that the value of theta, that is the argument of z, which satisfies this inequality, that is minus pi, is less than theta, theta is less than or equal to pi, is known as the principal value of the argument or principal argument. So here our theta 3 pi by 4, it satisfies this inequality, right? So now we have to find out the principal and general values of the logarithm of this complex number minus 1 plus iota. So now if we have a complex number z that is equal to x plus iy, then the general value of the logarithm of z is denoted by capital letter L, and here we write a log of z to the base e, and the expression for the general value of the logarithm of z is given by a log of z to the base e and plus 2n pi I, right? So this is an important result, and we have already discussed this result in detail in one of our video, right? So here the general value of the logarithm of a complex number z of this form x plus iota y is given by here log of z to the base e, and remember here we have the small l, and the small l represents the principal value of the logarithm of the complex number z, and here we add this term, that is 2n pi I, where n is some positive integer or negative integer or 0, right? So now here if we take z is equal to square root of 2 times e raised to 3 pi I over 4, then we can now write a log of z is equal to a log of here we have square root of 2 times e raised to 3 pi I over 4, and here we have 2n pi I. So here using the laws of exponents, we can now write a log of square root of 2 plus a log of e raised to 3 pi I over 4 plus 2n pi I. And here we have used this result, that is log of a times b, that is the product rule. So we have log of a plus log of b, right? So now here we can write square root of 2 as 2 raised to half. So we can now write half and log of 2. And here again using the laws of exponents, we can take 3 pi I over 4 in front of this log notation. So we have 3 pi I over 4, and here we have log of e to the base e and 2n pi I. And remember, n is a positive integer or negative integer or 0. So in these two expressions, we have used this result, that is log a raised to b is given by b times log of a. So now here we have half log of 2, and here log of e to the base e is 1. So here we have simply 3 pi I over 4 plus 2n pi I. So now we can write the logarithm, that is the general value of the logarithm of z, that is given by square root of 2 times e raised to 3 pi I over 4 as half log, and here we have 2. And now here we can take pi I common. So we have pi I, and here we have 3 over 4 plus 2n, right? So this expression gives us the uh, general value of the logarithm of this complex number, that is minus 1 plus iota. So now taking n is equal to 0 in this expression, we can obtain the principal value of the logarithm of minus 1 plus I, right? So here now we'll replace this capital L by small l, right? When we take n is equal to 0. So when we take n is equal to 0, then here we'll use small l. So we have log of z to the base e, and this notation denotes the principal value of the logarithm of minus 1 plus I. So here we have half log and 2, and here since n is equal to 0, so this term is 0. So we have here a 3 pi I over 4, right? So this expression gives us the principal value of log of minus 1 plus I to the base e, and this expression gives us the general value of log of minus 1 plus I, right? And whenever we write the general value of the logarithm of a complex number, we use capital L, and when we write the principal value of the logarithm of a complex number, we use small l, right? So n is equal to 0 corresponds to the principal value, right? And when we take here this integer n, then this entire expression represents the general value, right? So viewers, this is how we can find out the principal value and the general value of the logarithm of a complex quantity, right? And remember, whenever we find the principal and the general value of the logarithm of a complex quantity, we have to first convert this complex number into the polar form.